Everyone, I wanted to solve problem number 21 and 22 because they sort of go together, and I hope you notice that I picked out the same distance from the exact same large negative charge so that we can get kind of a better idea of what the potential looks like and what would exactly happen if we put a negative charge by this large negative potential, how fast something would shoot away from there. So the first one, problem number 21, is really just a straightforward application of the equation for what a potential looks like as a function of distance. So you can find this, of course, in your G and Coley. So for problem number 21, they're asking the potential from a certain point charge, minus 9 microcoulombs, when we're 59 centimeters away. So the first equation that I find that relates potential and distance and charge together is V, potential, equals K, Q, over R. Some of these equations look really similar. There's one that looks very similar for Coulomb's law and one that looks very similar for electric field as a function of distance. Make sure you got those separated out, but don't forget that on free response you'll be able to use an equation sheet. Anyways, plugging in, K is going to be 9 times 10 to the 9. That's a universal constant. Q is going to be minus 9 times 10. And remember, it's microcoulomb, so micro means to the minus 6. And then we're going to divide all this by 0.59 meters. We like meters in this class, not centimeters. Which will get you a rather large number, which I'm going to simplify and call 137,000 volts. So I'm going to write K for 1,000 and capital V for volts. Let me put a minus on there to keep things accurate because we're talking about a negative charge. Almost made an error. So now on number 22, we're going to put an electron 59 centimeters from this gigantic minus 9 microcoulomb charge. We're going to see what happens. So the question is, how do we translate potential into velocity? Well, you'll remember that in mechanics we would say if a hill is height h, then any kind of mass that would be placed at the top is going to have potential energy mgh. When it gets to the bottom, it's going to have kinetic energy of 1/2 mv squared. Similarly, with electric potential, we can say that at the bottom of this minus 137 kilovolt potential, the work that can be done, or that will be done on this electron, is equal to Q times V. This is one of your other equations from your textbook. So if we multiply by our potential and we multiply our charge together, then we'll be able to find out how much work, which by the work energy theorem will be converted into kinetic energy. We can find out how many joules of energy this electron will have as it speeds away. So if we say Q for an electron, which is minus 1.6 times 10 to the minus 19 coulombs, times our number up here that we got for V, it's about 137,000 volts. That and some change. We'll get a certain number. Now this is going to be set equal to 1/2 mv squared. So we can end up writing a general formula for the velocity that a charge will achieve. First of all, to get V by itself, we multiply QV by 2, and then divide by n, and finally take the square root to get rid of that square up by V. If you do all those steps, you should arrive at velocity, try to make that a small v, equals the square root of 2 times the voltage, capital V, put those serifs on there to make it look larger, times the small charge, Q, divided by M. Well, now, of course, voltage from above equals K times large Q divided by R. So we can modify this slightly and call that square root of 2K capital Q. Remember, that's our 9 microcoulomb negative charge, times a small q, our electron, divided by r, the distance it started out away from it, divided by m. The mass of the electron is another constant you can find in your Giancoli text, and that is approximately 9.11 times 10 to the minus 31 kilograms. Extremely small. Plugging in these numbers, we should get approximately 2.2 times 10 to the 8th meters per second. You'll hopefully recall that the speed of light is 3 times 10 to the 8 meters per second. So this is getting very close to the speed of light. Normally in these kinds of situations when we have very high velocities, we would have to deal with the theory of relativity, but that is not something we're going to worry about at this point in the semester. If you have any questions, feel free to email me or come by in person.